Good morning, good afternoon, or good evening, wherever you are located, and thank you for joining us for the April 2025 AMETEK Solid-State Controls webinar. And today we're going to be talking about the building blocks that I used within a UPS system. So as always, as everybody joins the room, I'd just like to ask if you can put in the chat bar on the right-hand side whether you can hear my voice or not. It would be appreciated because it makes absolutely no sense if I just speak to myself all day. So if you can just type in there whether you can hear my voice or not, it would be good. Thank you, London. I appreciate that. Thank you, Nathan. Thank you, Greg. Okay, so we can do the introductions while everybody else is joining us. My name is Craig Williams. I'm the Senior Technical Manager for AMETEK Solid-State Controls based out of the Stafford, Texas office. And Stafford is like a suburb that is southwest of Houston, Texas. I have 25 years in the industrial UPS industry. I used to work in the North Sea oil and gas fields. I worked with many different UPS and charger manufacturers, and this is my 9th year now with AMETEK Solid-State Controls. There will be a lag of around about 15 to 30 seconds between me saying something and you actually hearing my voice. Basically, the platform we use is Webinar Jam. It's got to process all the visuals and the audio and then send it out to iOS systems, to Windows-based systems. So there is some processing time that is taken to do that. So what that means is while I'm talking, if you hear something and you have a question and you type it in, I'm not going to see it until probably 30 seconds after I've been saying what I've been saying, which can get quite confusing and disrupt the flow of the presentation. So what I tend to do is I always ask people, if you look on the right-hand side of your display, you'll see a chat and a Q&A in the chat function. If you do have any questions, if you click on the Q&A only tab, then type in your question there. Then at the end of the presentation, I'll go into the Q&A only questions and I'll go through each one at a time, and hopefully I'll be able to answer the questions there. So that's the best place to put any questions that you have, is in the Q&A section of the chat bar. As I said, the platform that we use is called Webinar Jam, and it has a panic button. So if I see some comments coming in that you can't hear me, or you can't see the presentation, or there's something wrong, then I can press the panic button and everybody will be transferred into a brand new room and we will continue as if nothing has happened. Another very popular question is, will the webinar be recorded? And yes, the webinar is recorded by Webinar Jam. And if you have registered, which obviously you have if you are listening to me now, if you have registered for it, you will get a link after the webinar has finished to go and view the webinar again using the Webinar Jam platform. The only problem with that is they treat it like a live webinar. So if you press play, you can't fast forward, rewind, or do anything like that. You've got to watch it as if it is a full webinar again. So what our fantastic London marketing department does is London takes that video, converts it to an MP4, and then uploads it to our Solid-State Controls YouTube channel. And that video will be available by the end of the day, and you will receive a follow-up email with a survey and the video link. Okay, so that way, if you go to the YouTube channel, you can play, fast forward, rewind, go past any bits that you think are boring, which for many people is quite a lot of it. I'm only joking. You can send it, share it, do whatever you want with the video. It's a public link, so you can share it with whoever you want. And the webinar should last around about 1 hour, once again, depending on how much I talk and how much how many questions we get at the end of the webinar. So that's all of the introductions done. So I suppose we better get started. So the learning outcomes today is hopefully understanding the following blocks of a UPS. So the four major blocks are the charger rectifier section, the inverter section, the static switch section, and the MBS or RMBS, and that stands for maintenance bypass switch or remote maintenance bypass switch. It could be manual bypass switch or remote manual bypass switch. The terms are interchangeable, but it is a switch that allows you to move the system into bypass physically rather than through the static switch. But we'll explain all of that as we go along. So here on the screen now, you will see a what we call a general single line diagram of one of our systems. Okay. This is the overview of how our systems work. And the red line here is power flow. Okay. And the yellow line up here means it's energized, but power is not flowing through that path. It's ready, it's available if necessary, but it's not flowing. So normal power flow is from the grid supply, which is usually a 3-phase 480 volt supply in North America. And that goes into our system through a transformer and then into our rectifier charger block. That rectifier charger block charges the batteries at the correct voltage, and then it goes into the inverter, and that DC is then converted back into AC. That AC goes through our static switch. SSW stands for static switch, and this is the inverter static switch. And power will then flow through our maintenance bypass switch out to our load circuits, okay? And the purpose of the UPS is to maintain power to the load circuits even when grid power goes off, okay? So that is the main power flow. That is what the UPS will try and maintain at all times. It will try and keep the power flow through the inverter as much as it can, because the inverter creates a perfect sine wave that is unaffected by anything that goes on at the AC input or the bypass input, okay? It takes the DC, converts it into AC, and creates a sine wave that the load circuits can use for uninterrupted power. So the first block that we're going to talk about in the major blocks inside of a UPS is the rectifier charger, okay? And that's what you can see on the screen here, highlighted in red. And it takes AC and it converts it to DC in its most simple form. Now we have to go into a little bit of how it does that. So for ease, the easiest rectifier that you can get is a half-wave rectifier using a diode. Okay, that's the diode there. And if you know anything about a diode, you should know that it allows power to flow in one direction and prevents power flowing in the reverse direction. And power flow when the anode, so this side here is the anode. If the anode is more positive, so let me write A for anode there. If the anode is more positive than the cathode, so we'll do C here for cathode, then that will allow power to flow, okay? So therefore, this portion of the sine wave here, because that's going into this transformer here, the sine wave is more positive from that side with respect to this side, and the transformer transforms that voltage, so it is more positive with respect to that. So in this case, power will flow through the diode, through the load resistor, and back to the negative portion, because remember, in an electric circuit you have to complete the potential from positive all the way through to negative. Okay, so it will allow that part of the waveform through. But when we get to this section of the waveform here, we now go positive with respect to negative here. So that makes this positive with respect to negative here. So power tries to flow through our load resistor and back through this diode. And this diode says, no way, that's not the way that I work. I will not allow power to flow this way. It says no. Okay, so therefore none of that waveform flows through the resistor. And as you can see on the right hand side, this is the resulting waveform. This diode will allow the positive cycles of the AC signal through, but it will not allow the DC, the negative cycles, my apologies, the negative cycles of the sine wave through. So the big question is this waveform here, is it DC? And I hear you all shouting at the screen. Yes, no, I don't know. Well, the answer to the question is yes, it is DC. It's actually called pulsating or pulsing DC, because all this voltage here is positive with respect to negative. The only thing that changes is the amplitude. So the current flows in that direction for both waveforms at all times. It's just how much amplitude or how much potential there is behind it. It's only how much potential is behind it that's changing. The voltage is changing. The direction of current is not changing. So this is called DC, direct current. The current is only flowing in one direction. And it's very important to know that's how a rectifier works as we go through the further slides and understand what a charger rectifier is actually doing inside of a UPS. So hopefully you understand this portion here. Now then, there is this wordy sentence here, and you can search the internet. Basically, that's what I Googled it, because I have a certain amount of data that I can store in my brain, and then eventually it just gives up. So Google is my friend. But with a one diode half wave rectifier, the average DC voltage on the output is approximately 3.318 times the peak AC voltage, or 0.4 times the RMS AC voltage. Okay, so basically what that sentence is saying there is, if we know what the AC input is to a rectifier with one diode, then using this calculation, we can figure out what the output is on this side, the average output. Okay, so if we use a calculation for 120 volts, the output would be 54 volts DC. Okay, but, and this is very, very important, if the AC input voltage changes, and let's say it went up to 150 volts, then the output, the resulting output voltage would also change. The average would go up to 67.5 volts. Okay, so although this rectifier, yes, it is converting AC into DC, what it's doing is it's passing any change in that AC on to the output DC. So if the input voltage changes, the output voltage will also change. Okay, and the question is, what is the main purpose of a charger? And you should all be shouting at the screen, the main purpose of a charger is to charge a battery. So that is the main purpose of a battery charger, is to charge a battery to store energy. So if there is a power failure, we can use that energy stored in the battery to supply our loads. Okay, and there's one important thing that you need to know about batteries, and that is they need to be charged at a specific voltage. For lead acid batteries, it's usually 2.25 volts per cell at 77 degrees Fahrenheit. Now, some manufacturers have different voltages, but that is what the lead acid manufacturers usually say, roughly 2.25 to 2.27 volts per cell at 77 degrees Fahrenheit. And if you go out with that voltage, then you're going to undercharge the batteries or you're going to overcharge the batteries. So if we go back to this diagram here and we only use the diode and we put in the correct voltage here to get the correct voltage for our battery, which will usually be 135 volts for a 60 cell system. Sorry, my writing is terrible. Okay. If that voltage went up or down on the AC input, the voltage going to the battery is also going to go up and down. So we're going to be undercharging or overcharging the battery with any fluctuation in the AC input. And remember, as a charger manufacturer, we cannot guarantee what the AC input is going to be. You know, in North America, we stipulate is 480 volts. But we know at this facility here in Stafford, Texas, it usually runs around about 500 volts and it changes throughout the day. And that's the same in most plants. The voltage is going to be a certain voltage, but it can change throughout the day. So therefore, we have to come up with a way to be able to maintain a steady output DC with varying AC inputs. And the way that we do that is instead of using a diode, we use an SCR. So this is the symbol for an SCR. And that's a silicon controlled rectifier. Okay. Now, once again, this isn't the design of our charger yet, but it's a very simplified version so you can understand what's happening. And the rules of an SCR is basically it is a diode that needs permission to turn on. Let me say that again. An SCR is a diode that needs permission to turn on, and that permission is given through its gate lead. If you do not send a gate signal to the SCR, then it acts as an open in both directions. It's if it's an open. It will not allow current to flow in either direction if you do not send it a gate signal. Okay? And then when you do send it a gate signal, then what it's saying is, okay, now you are allowed to become a diode. So therefore, all we're saying now is you are a diode, so therefore the anode has to be more positive than the cathode to allow current to flow. So if we put this waveform through here, we would get this waveform out here. But the only difference is we can tell the SCR when to turn on at any point in this sine wave. Okay, so when you see this sine wave on the output here, or this pulsating DC, that means at this point here we have turned the SCR on and we have allowed the whole waveform to get through. But the thing about an SCR is you can't turn it off by removing the gate signal. Okay, one of the inherent properties of an SCR is once you turn it on, the only thing that will turn off an SCR is when the potential between the anode and the cathode is 0 volts or close to 0 volts. It's actually usually around about 0.3 to 0.5 volts. It's called the holding voltage. Once it drops below that voltage, then it will automatically turn itself off, or when current stops flowing through the SCR. Okay? And the good thing about what we're trying to do with the rectifier is we're using a sine wave, and at every single point where it changes direction from positive to negative, we have what's called the zero crossing point. And at the zero crossing point, the voltage on the anode is 0, the voltage on the cathode is 0. There is no voltage, no current flowing through the SCR whatsoever. So every time we get to the zero crossing point, the SCR will switch off. and become an open in both directions again until we send it another gate signal. That is how an SCR works. Okay? So therefore, what we could do is if we said at this point here, that's when we turned the SCR on, then the output waveform would actually look like that. This portion here would not be allowed to get through, but this portion here would until that zero crossing point where it waits for the next signal. Okay, here's another example where we're showing you where we are turning the SCR on. So these are the gate pulses that are being sent to the SCR. Okay, so if we started the gate pulse at this portion here of the sine wave, then the actual output is going to be here. Okay, if we turn it on at this point here, if you follow the line down, you're only going to get this much out. And once again, if you turn it on here, you'll get this much. And if you turn it on right at the end, you'll get this much here. Okay. So the size of the gates signal never changes, just where it is in the sine wave changes, and that affects our output. So obviously in our chargers, they're a bit more complex because they are three-phase chargers. We have A, B, and C phase. And then what we use is we use 6 SCRs. 1, 2, 3, 4, 5, 6. Okay, and that allows us to convert both the positive and negative going sides of the AC waveform into DC. Okay, which will become a little bit clearer on this page here. Okay, so when we send a gate signal to the SCR and the red is saying A phase to B phase, okay, it's saying, okay, this is the portion here that gets through. And then the next gate signal comes B to C phase at this point here. And if you follow that down, that gets this portion here. And then this portion here is C to A. And that gives you this portion here. And then it repeats over and over again. And as you can see, the output waveform from the AC input voltage here to our rectified DC output voltage here is now much more like we would expect to see. It's much more like DC. Okay, it does have a ripple on the top of it, but it is much more like DC. There isn't any missing gaps on that. Okay, and what fills in those gaps? Well, what we do is we use an inductor and a capacitor, an LC filter. And if we put a sine wave into, sorry, not a sine wave, a rectified AC sine wave into an LC filter, this is the resulting signal. Because what the capacitor is doing is basically it's charging up at this portion here of the sine wave, and then it discharges until we charge it back up again, and then it keeps on discharging. So the capacitor is kind of acting like a short-term battery. It's charging and discharging, charging and discharging. And then the inductor, basically, an inductor resists a change in current. The field across the inductor energizes and collapses with the current going through it. And what it tries to do is keep the current flowing steady. It doesn't like a change in current is what I'm trying to say. And both together create a very good filter that fills in the gaps of the rectified output and smooths it out. And the more capacitance and inductance you use, the smoother the filtered output is. So hopefully that helps you understand a little bit more about how a charger works. And now we're going to discuss inverters. So what does an inverter do? Well, it converts DC on this side into AC on this side. Okay, if we go back to this screen here, you can see the symbol here. We've got DC on this side and AC on this side. That is what an inverter does. It converts DC into AC. So if I drew this and I take it out here and I drew a battery out here, you know, this is the sign for a power supply, but it's a battery, whatever you want. All we need to know is that we have positive and negative here. And if we stick with the 60-cell lead acid system that I was speaking about earlier, we're going to have approximately 135 volts going in there. Okay. And what we use in our DPP UPSs here at Solidstate Controls is an H-bridge. Okay. An H-bridge is something that looks like an H. Okay. That's basically what it looks like. No, I didn't want to do that. Sorry. Just getting my pencil working again. Sorry. So we've got 135 volts going in here. So now we have 4 switches. We have S1, S2, S3, and S4. Okay. And this will become a little bit more apparent as we go through. And what we're going to do is we're going to have S1 and S4 closed. They're going to be turned on. Okay. And what that allows is this positive voltage here to flow down here, and get to this side. And we're going to say that this is a motor. Okay. So this side of the motor is going to be positive. And with S4 closed, negative is going to go to this side of the motor. So we've completed the circuit and the motor will spin clockwise. Okay. Which is good. But what the fascinating thing that we can do with an H-bridge is we can change the polarity of that motor and make it spin in the reverse direction just by opening the first 2 switches and closing the next 2 switches. So we've now opened S1 and S4, and now we've closed S2 and S3. We haven't changed the polarity here. So we're going to use the positive, and now instead of the positive going down here, it's going to go this way, and it's going to make this side of the motor positive, and this side of the motor through S2 is going to be negative. Okay, it's negative there. And that will make the motor spin counterclockwise. So we now have a way, just with switch arrangements in an H-bridge, to change the polarity on the sides of the motor to make it spin in a different direction. And that's very handy because a motor is very similar to a transformer. It's a coil. So what we can do in an inverter is, instead of using switches, we use IGBTs, which is an insulated gate bipolar transistor. And instead of a motor, we are going to use a transformer. Okay. And hopefully in the next page, you'll understand that in the next few pages. So an IGBT is this device here. We have a gate, we have a collector, and we have an emitter. Now, near enough all IGBT manufacturers have this diode built internally into the IGBT. And the only reason that's there is for any inductive kickbacks. It allows any inductive kicks to be then discharged back into the capacitors back on the DC bus, and basically prevents the IGBT from blowing up from back EMF from inductive kickbacks because of the switching of the IGBT. But basically, the circuit equivalent of an IGBT is similar to this. Okay, we have our collector here, we have our emitter here, and we have our gate is your finger, and we have a spring switch here. And if you send a signal to the gate, it's the same as you pushing your finger against this switch and closing this circuit. The collector and the emitter are connected together. The switch is on. We don't use the transistor in any of its fancy linear regions to amplify in a certain way. The way that we use IGBTs is either on or it is off. So it's just like an electronic switch, okay? And then what we do, we still have an H bridge here, okay? But now what we do, instead of having switches, we have transistors. And we're going to label them in pairs. So we have A and A here, and then we have B and B here, okay? Now remember we had the motor here, okay? What we've done in this drawing here is we've taken the motor and we've extended it out and we've turned it into a transformer. It's still the exact same drawing you saw in the previous slides, but now we've just moved it out of the drawing because that's how we draw it in our inverter bridge at AMETEK Solidstate controls. So remember, we've got A, and we're going to switch A transistors on, and remember we've got positive and negative here. So if you follow it down through here, you will see this side of the transformer is positive, and then this side of the transformer through this transistor gets down to negative. So this is negative, okay? So with A transistors on, we have a positive with respect to negative field on this transformer here, okay? And then we switch the A transistors off and we switch the B transistors on, and once again the polarity of our DC has not changed. It's still positive here, but now the positive goes through the B transistor down here, and this makes this side of the transformer positive. And if you follow this down through this transistor here, that makes that negative. So we've now reversed the polarity of this transformer by switching the other IGBTs on. So basically, what that allows us to do is we can create in our UPSs on our DPPs a pulse width modulated transistor waveform where we can have positive pulses and we can have negative pulses. And if you took a mathematical average of those pulses, you would see that it roughly creates a sine wave mathematically. We do have to do some filtering to actually turn it into a sine wave, but mathematically using pulse width modulation, using the averages, it turns into somewhat of a sine wave, okay? So what you get is you have on the primary of the transformer here, you will get the pulse width modulated waveform that kind of looks like a square wave. And then because of the inductance here and the inductance in the transformer here, and because of this capacitor here, the output that you will see coming out of this transformer will look like a near perfect sine wave. Yes, if you zoomed in on it, you would see some little sawtooths like this, depending on how good the capacitor and inductance circuit is to filter out any harmonics. But that is what we're doing. The inverter is simply using this pair here and then this pair here. We just switch them at 8 kilohertz within our inverter bridge, and that gives us a perfect 60 hertz sinusoidal waveform on the output. So we've talked about the charger, we've talked about the inverter, so now we're going to talk about the static switch. Okay, so SSW on our drawing stands for static switch, and all of our UPSs have 2 static switches. We have an inverter static switch and we have a bypass static switch. And we will move on to explain how they work. So once again, using the same theory as we did for our rectifier, and if you look, these symbols here are an SCR, but they are connected back to back. We'll get to that in a moment. So we have an SCR here. And if we fire that SCR right at the start of the sine wave at this point here, then that is going to allow that whole portion of the sine wave through until we get to the zero crossing point. Okay, and then if we fire the SCR at this point here, remember, sending a gate signal to an SCR only tells it to start being a diode. So we allow this portion of the waveform here and this portion of the waveform here. But remember, it can only be a diode, so we can only allow current to flow this way here. Current will not flow back this way here, so this portion of the sine wave is not getting through. So we have to do something about that, because a static switch has to allow both sides of the waveform through. If you look at the picture here, you know, our output here is a sinusoidal waveform coming out of the inverter, and both that side and that side need to get to the other side of a static switch here. So we don't just have one SCR, which would only allow basically that to get through. We have two SCRs that are going to allow the other side through. And I'll explain how we do that. So now what we do is we have another SCR that's connected on this side. Okay. And if we switch this SCR, because remember, this is going to be positive with respect to here, positive with respect to here. So if we turn the SCR on at this point here, the anode is going to be more positive than the cathode. We've told the SCR it is now allowed to be a diode, and it will allow this portion of the waveform through, because that's when the gate signal happened. Okay? So all we have to do is figure out how we can have two SCRs connected in a certain way to allow both sides of the waveform through. And the way that we do that is we connect them in what's called inverse or reverse parallel. We have one SCR anode to cathode here, and we have the bottom SCR with the anode to cathode in the reverse direction. So this SCR allows current to flow that way, and this SCR allows current to flow that way. So as long as we switch on the SCRs at the start of every single part of the sine wave, we will get the full output on the output here. And basically, it is just an electronic switch. So if the switch is open, if we don't send a gate signal to the SCRs, the switch is open. We do have AC input on this side of the switch, but because the switch is open, you have nothing here. And then what happens is if we have the switch and if we then close that switch, then the output here gets to the output here. Now, obviously with a switch, there is always going to be moving parts. Moving parts are unreliable, okay? And moving parts are slow, physical moving parts. And they allow arcs to jump as soon as they get close. And they can cause pitting of the terminals. There's a lot of issues that happen with a switch. With a static switch, with an electronic switch, none of that is a problem. There are no moving parts. There's no arcing when we switch them on and off. There is no wearing. There's no time delay. You send a signal to the gate and it switches on instantaneously, basically. Okay, so that is what a static switch means. It doesn't mean there is static electricity. It is a switch that has no moving parts. It is static, no moving parts. Okay, that's what a static switch does. And we just send a signal to both gates and it allows it to turn on. And then we remove the signals and it will turn off when we get to a zero crossing point. Okay. And actually, what I do before I go on to the maintenance bypass switch. That's quite an important point, that you can remove the gate signals from the SCR, but remember, let's say we remove the signals from the SCR at this point here. Remember what we said in SCR, it will still carry on conducting until it gets to this point here, okay? And that's actually a very good thing when it comes to a static switch. Because in theory, what you actually have is you have your inverter static switch and you have your bypass static switch. Excuse my drawing once again. And they are usually connected together like this, and they go out. And we have a waveform that is in synchronization. So this is the bypass, and this is the inverter. And what we can do is, when you press the inverter to load button on a UPS, sorry, the bypass to load push button on a UPS, and let's say we pushed it at this point here, this portion here of the inverter carries on conducting. And if I go up here, and then this portion of the bypass, if you follow it down, will conduct as well. So they'll conduct in parallel. So what that allows us to do is have a seamless transfer every single time between bypass and inverter to bypass when they are in sync, because you cannot switch an SCR off. It will only switch off when it gets to its zero crossing point. So whenever you turn it on, you are going to have two AC supplies in parallel for a very short period of time, which gives you the security of knowing that your loads are going to be maintained at all times. Hopefully, I made that clear. Excuse me just a moment while I take a drink before we talk about the maintenance bypass switch. So the maintenance bypass switch is obviously this block here, the one that is in red, okay? And there are three positions on most of AMETEK solid-state controls bypass switches. Now, it does vary with age and design, but in truth, most modern-day bypass switches that we create have a B, which is bypass. Actually, it shouldn't be B. That's my, I shouldn't have drawn it like this. It should be N for normal. My apologies. N for normal. I should really fact check my slides before I do my presentations. Okay, so we have normal, then we have BTL, which is bypass to load, and then we have BI, which is bypass isolate. Okay, so in the normal position, let me just do this, normal, normal, and normal. Power will flow out from the inverter through the static switch, out through this bottom normal contact here, which is closed, out to the load circuits. Okay, that is the main power flow. But our bypass supply is allowed to go down through this contact here, which is the normal contact, out into our bypass static switch at this point here. Okay, so it's ready and available. So if somebody wants to press the bypass to load button, or if the inverter fails, we can turn the bypass static switch on and allow power to flow through this way here if we need to. Okay, so that is the normal position of the maintenance bypass switch. Now the next position is bypass to load. Okay, now before we go to bypass to load, and I'm always going to have this normal here, before we ever move the switch from normal to bypass to load, we always have to make sure we press the bypass to load static switch push button. It's very, very important, because that way we are always paralleling when we move this switch between normal and bypass to load. It's a make before break switch. So therefore, there is going to be a point where the power on this line here is going to be the same as the power on this line here. And if we make those both bypass by pressing this bypass static switch button, then we are paralleling bypass and bypass together. And therefore, the waveforms are always going to be perfectly in sync because they are the same. So you can never have an issue. So whenever you move the physical maintenance bypass switch from normal to bypass to load, you always want to press the static switch bypass to load button. And all of our procedures on our UPSs tell you that, okay? So once you have pressed bypass to load on the static switch, then we can actually physically move the switch to the bypass to load contact, which is this middle contact here. And what that does is, remember, it's make before break. So it actually makes this red line here goes down through here, through this contact here, and out to the loads here before breaking this contact here. Okay, so it makes this contact and then breaks this contact. And at that point there, the red on the screen here is the power flow. All of this is energized, but it's now no longer supplying any power to the loads whatsoever. And in this situation, if you had an AC input failure and you were hoping to go to battery, you're going to lose your load, because if the AC input and the bypass input fails, the battery has no way, because we've opened this switch here, has no way to get to the loads whatsoever. So once you move the maintenance bypass switch to the bypass to load position, you are on bypass, and that is it. You have to rely on that bypass supply. And then the last position is the bypass isolate position. Okay. Once again, it's a make before break arrangement. And all it's doing is, nothing changes down here because we were at bypass to load before, and now we're at bypass isolate. So there is no connection at this point here. Now, rather than go through this bypass to load connection, we are now going through the bypass isolate connection here. But more importantly, at this bypass isolate here, there is no way now that the bypass input can get through here and get back to the static switch, okay? Because we're now going to this contact here, and that is not allowing power flow back into here. So basically, when we say bypass isolate, what we mean is we're isolating the bypass from the bypass input to the UPS, okay? And there's a very good reason for that. And what that allows us to do is, when we're in the bypass to isolate position, there is no power here. This is the bypass input to the UPS. There is no power here. That is the output of the UPS. We can go to the MCC that supplies this AC input here and lock it out and tag it out. And then we can go, let's draw this out like this. Let's see the battery is external here, okay? And there is a disconnect. We can lock out, tag out that battery disconnect there. And what that allows us to do is make this whole UPS cabinet volt free, so we can do intrusive maintenance. We can clean it out. Or if we really needed to, if this UPS was obsolete and it needed to be replaced, we could disconnect all the cables here. We could disconnect the battery cables here, these cables here, and these cables here. And we could remove this UPS and then install a new UPS and connect all the cables back up again, test it, make sure everything's good. And then following the procedure, we could put the bypass switch back into the normal position. And you could do this in theory without losing power to any of your load circuits. So that is the true advantage of having an external or a remote maintenance bypass switch. It allows you to make the UPS completely volt-free so you can do intrusive maintenance or indeed replace it. So that is an RMBS. So that basically brings us to the end of the presentation today. That is the 4 main building blocks of the UPS. And now I'm going to go to the chat and to the Q&A. And it is at this point here, if you have any questions whatsoever on what we have discussed so far, we'll use the last 10 minutes of this webinar to go over any of those questions. So if you have a question, just go into the chat function on the right-hand side. And then type in the Q&A section any questions that you have. And while we wait for those questions to come in, if indeed there are any questions, I will let you know that London has done her due diligence, as always. She's wonderful. She's put in the links to our webpage. Our webpage is www.solidstatecontrols.inc.com. If you just click on the link that she's provided, that takes you to our webpage, and there's a contact us. It gives you everything that we do, training, all that kind of good stuff. And if you fill in the contact us page, it will always get to the right person to answer your questions. Okay. Also, the YouTube channel link is still in the chat bar there. So later on today, this video will be converted into a YouTube video, and you will be able to share it, pause it, rewind it, fast forward it. And really, most importantly, if you see the bottom of the chat bar there, it says, please take 2 minutes to complete our survey about this month's webinar. And it's not because we're really looking for metrics, although we do want to know what you think about each webinar. But what we really want to know is, I think it's question 5, what would you like to hear from us at our next webinar? What topics would you like us to discuss? So if you have an opinion and there is something that you struggle with or something that you are more interested in hearing about, then please put that in that every single survey to find out what people want us to discuss at the next webinar. And I promise I will look at it. And also there's our 1-800 number. If you want to speak to a human, then you can also call 1-800-635-7300 and you will get to speak to one of us. So somebody has asked, what's the purpose to have bypass to load? That's a very good question. A very good question. So let me go over that. Why have the bypass to load position, and why not just have a normal and bypass isolate? So let's go back to the bypass to load position. The reason we have the bypass to load position is we're disconnecting the inverter output from the loads, but we are still connecting the bypass input to the static switch inside the UPS. And what that allows us to do is that allows us to do some testing of the UPS without affecting the load circuits. So if we've done an intrusive maintenance on the UPS, we've replaced the capacitors, all of the control boards, we want to make sure when we power that UPS back up again, that the static switches will operate correctly. And what we can do in the bypass to load position is we can go bypass to load or inverter to load using the static switch and test those functions. We can even put a load bank on the output of the system here. We can put some resistive load on the output here. and load the UPS up to 100% load if we really wanted to. What basically the bypass to load position allows us to test the UPS before going back to the normal position after we've had some intrusive maintenance. So very good question, but that's why we have the bypass to load position. It allows us to do testing of the UPS. Okay. You are very welcome for the explanation. And do we have any other further questions? It's not like me to finish early and not have any questions to answer. Would the load be automatically switched back to normal source if there's a loss of bypass source? Very good question again. I love these questions. That's why I always leave time at the end for these questions. So let's go back to that slide. So it's not that one. Is it this one here? Yeah. So we're in normal position on the bypass switch. Okay. We're on normal position, but we have pressed bypass to load on the static switch. Okay. So power is flowing from the bypass down here through the static switch here and out to our load circuit. So the question is, would the load be automatically switched back to the normal source if there's a loss of bypass source? AMETEK solid-state controls design principles say, no, it will not. And the main reason for that is somebody has to physically press the bypass to load button. And if somebody has pressed the bypass to load button, that means they are probably starting a switching sequence to put the system into maintenance operation and do some maintenance on the UPS. So our principle is, if somebody has told it to go to bypass, then there's a reason for it. So therefore, if we had an automatic switch back to the inverter static switch, if the bypass failed, then that switching procedure would be confused, it would be messed up, and could, in theory, put somebody in danger if you're going through a lockout tagout process. So for our UPS, once you are in static bypass, once this static bypass is on, if the bypass input fails, it does not transfer back to inverter. Your load circuits would be lost. Okay, so it's a very good question. We are having internal talks where using the software, the end user can select which theory of operation they would like. Because if the system automatically transfers to bypass because of an overcurrent situation or something like that, if something automatically transfers to bypass, then yes, if the bypass does fail, it will transfer back to inverter. But if auto transfer is switched on, I have to make that clear. But if somebody presses the bypass to load push button, then it will stay in bypass even if the bypass fails. So yes, as I said, we are discussing internally whether we should allow the customer to say, okay, you can have mode A of operation, which is what I just explained, or you can have mode B whenever the static bypass is on. If the bypass fails, then the inverter will take back over again. And then it will be the customer's choice which mode of operation they would prefer for their plant, because they may turn around and say, you know what, all I care about is this load. I never, ever want to lose power to this load. So I would prefer, even if somebody was going through a lockout tagout procedure, I would always prefer my load to be supplied. And that way there you would choose option B, where it does transfer back to inverter to load. if bypass was lost? So once again, very, very good question. Okay, I think that is 11 o'clock. Hopefully that explained all the questions that we have had. I would like to take this time to thank you very much for joining us for this April 2025 webinar. I hope you learned something. I hope I explained it in a way that made it easy for you to understand. And I know that your time is precious, and for you to take an hour out of your day to listen to me and to listen to our presentation, that doesn't go unnoticed. We really, truly appreciate that. Lucas has asked, is there PDH certificates? We don't have an accredited way to give PDH certificates, unfortunately, at this time. We are working on it, but not at this time. But once again, thank you very much for joining us today. And until next month, take care, stay safe, and we look forward to speaking to you again. Thanks very much, everyone.